Welcome, everyone. While people are getting set up, I'm going to remind us a little bit, situate us in the recent coverage. So we noted we're going through successive topics related to uncertainty in agent-based models, most of which carry over directly to topics for other types of dynamic modeling. Today, in the lab session, as promised, we're going to be engaging in some hands-on exploration involving calibration. And to that end, I'd like you to fire up your AnyLogics, and I will share my screen and switch over to a view of that on my own. Specifically, when AnyLogic comes up, it may present you with a set of example models. It's possible it will show you this welcome screen when you are bringing it up. If it doesn't, you can go to Help Example Models, and it will allow you to see this set of example models, some of which we've provided the key contributions. Now, I'd like you today to go to this one called SIR agent-based calibration. And we're going to explore it, but we are explore it as given, but we will further be working to modify this model in some ways as time allows to secure better understanding how model structure impacts model calibration, with the ability and fidelity with which we can calibrate a model. But if you click on that and open it up, you should have loaded in a model such as this one. It consists of a main environment, which captures some information that will be important in the calibration, these data sets. And it further provides some information against which we are calibrating the model. Information on, in this case, the number of infectious people that we're seeking to match. Sort of, this is empirical data on the number of people recorded as being in the infectious state, say infective, every 2 time points, 2 days. And you can graph that out in the preview. This is what's called a table function, and it's a handy way for characterizing data that specifies for different values of the input what output we wish to achieve. I will note, for those interested in building blocks in this particular platform, that some of the affordances offered by this compared to hand coding it is that it provides options for handling out of range, so things outside the specified domain of the function. In other words, here, values, if you gave it, so the idea here is this stable function, if you give it a given value, let's say 8, it would give you back 71. It's a mapping, right, from the domain to the range, from the argument to the value, using its terminology. But this out of range allows us to say, well, if we passed in a value less than 2 or a value more than 200, what value, how should it handle that? Should it give an error? Should it give the nearest one that is in here? should it just sequence here like that, whereby we assume that the sequence repeats precisely after each of these ends? Do we wish to handle it with some custom value, or do we wish to engage in some sort of extrapolation, which I suspect is linear extrapolation, although we'd have to check the documentation. We're going to leave it as error. So if we give it a value outside of that, it'll indicate an error. We further have the option for interpolating values. Here, extrapolation would be taking the values that you have and projecting them, as it were, outside of that range. So if we had an outside range, that's why it's in this out of range, it would project outwards, probably in a linear fashion, conceivably in a more sophisticated fashion, such as spline-based. It would project what it is. By contrast, interpolation is talking about, it's not extrapolation outside, it's interpolation. It's figuring out, if you give a value, for example, which was 193, how would it decide what the value is for 193, right? Or if we gave a value of 7 as the input, how would it determine what value to give back? And here you have a choice between having a step-based, so I believe this would be, if it's 7, it gives 24, because that's the one prior to that. You could see the little steps here. By contrast, linear would make these piecewise linear, right, between each of these points. Here we could do a spline-based interpolation, which would support some more curvilinear features, but anchored at certain points. We could also have an approximation to this of a certain order, and I won't fill in exactly what that is, but we could try to interpolate it. We're going to keep ours at linear. So just assume a line between these two. So if we were to give 7, it would give the average of 24 and 71, right? Or equally much so, it will give 24 plus 71 minus 24 divided by 2. Same thing as the average of those two. Okay, anyway, this is our so-called historic data we're trying to characterize. Those here will recall from this, from our discussion yesterday, and I should actually have it up here, that we are in calibration, seeking to adjust less well-known model parameters, right? To best match observed data. We've just looked at our observed data. We will be tuning less well-known parameters to match said data. We specified the data to match. Now we have to specify, well, it's not a sequence, but we do have to specify the range over which to vary them and which parameters to vary. That's specified in this calibration experiment. So here we're going to be adjusting contact rate and infection probability, which I think is somewhat silly for reasons I'll talk about in a few minutes. But we're going to be considering values for them for contact rate 0.5 and 5, and for infection probability 0.1 and 0.8. Now, this is like exploring, and forgive me, in this case, what would be a 2-dimensional plane, right, where this might be contact rate and this is infection probability, and we're adjusting assumptions about them. And every point on this plane, for our case here, because we only have 2 values, we don't have a 3rd dimension, for each point here, we're going to compute how good a match is there between the model output on the one hand and that data we saw, this data. And we're going to be trying to adjust those parameters to find the best point within this plane, the point where they match most closely. Okay, so we've seen specification, what data to match, what parameters to vary. Now we're going to need to specify how good or how bad is a given match. I'm going to speak about the discrepancy metric, right? The metric by which we assess how far off is the model's output from this data we're trying to observe. So that's going to be specified here in the calibration experiment in this objective function. Okay, it's calling off to a difference function. Okay, and this difference function, don't do this at home, but I'm just gonna type this here and use autocomplete so that I can see the definition of it. Difference function, always non-negative. Yes, that's one of our desiderata, right? It should be non-negative, right? Difference function. Okay, now I lost the tooltips here. Difference function, non-negative, reflects the difference. Yeah, okay. In what sense? Between the given data set and the table function. And you'll notice it returns a value that's the square root of the average square of the differences between the linearly interpolated data set from the model and the table function. So we're giving it this table function we've been looking at, this historic data, and it's taking the average mismatch for each of these points, each of the points within this, and I believe actually it'll be for 0, 1, 2, 3, 4, 5, not just those. And no, excuse me, it would be for these particular time points and what the model gave. And as it says, taking the average square of the difference between those. So it's like taking the difference between each, between what the table function gives for a given time, what the model gives, squaring it, taking the average of those to take you the square root, or you could think of it as summing up all of those, dividing by the number. So if you had three data points, summing those up for each of those 3 data points, that square of the difference between what the model gives and what the empirical data gives, summing those up, the squares up, divided by 3, take you the square root. And for those familiar with statistics, when you have a metric to measure discrepancy, often there's some sort of error model that comes along with this. And I believe from much past discussion that this is associated with the assumption of normally distributed error. This some square of differences. So here we're taking that. I'm going to restore that to this. So again, this is the data from the model. This is the data from the historic. This data we're providing exogenous. We're saying match this, right? Okay, so we're specifying some discrepancy function. Suppose there were more than one thing we wanted to match. What would we do? Well, we'd simply sum them up as long as they were in comparable units. We can't add people to dollars to, vials of vaccine to doses, right? We need to make sure that they were appropriately scaled to be dimensionless, to have unit dimension, that they were fractional quantities or proportional quantities. You can add up quantities of unit dimension, but it is semantically meaningless to add vials of vaccine, error measured in being off by a certain number of vials to vaccine to being off in a certain number of people who might have, developed the illness, and off in terms of the dollar spent or what have you. Okay. And then characteristics of the desired optimization or tuning algorithm. That's this so-called opt quest, which is widely used software for global optimization that can be used for many purposes, including policy optimization. Indeed, there's a policy optimization type of experiment here in okay, that's interesting. There's a type of experiment that's a optimization you can perform that's commonly used for policy optimizations. Okay. And here we're using it for calibration. We're trying to minimize this function rather than trying to maximize some measure of goodness. If we put a minus sign in front, we could maximize it, right? Okay, so this is the idea. Now, where does this DS infectious current come from? Well, it comes from running the model. Let's go explore where that is in the model. Well, it's in the calibration experiment. There's a thing called DS infectious current. So the fact that this mentions DS infectious current is a reflection of the fact that it's right here in the calibration experiment. The conceptual idea here for the setting this up is going to be quite similar to what we did for sensitivity analysis. Specifically, we're going to be running the model again and again, successive runs. We are going to take this DS infectious current after each simulation run, fill it with the values that actually were recorded in the main experiment. And by so doing, we're going to have available to us in this DS infection current the ability to compute this difference and adjust it. And then after we run the model all the times that need to be run for a particular assumption about this here, for a particular point within this, we would then compute whether or not it's the best such iteration. If it's the best such iteration, we will record that as the best so far. And that's so that we can record what particular values of the two parameters being optimized yield the best match to the empirical data. Okay. So this is something which goes on once we have run all realizations associated with a particular set of parameter values. That criteria about doing this after the iteration is a reflection of the fact that we're going to be running here for each set of parameter values, the model, not just one time, but for a set of realizations, an ensemble of realizations. In this case, 5 realizations. We do that because of stochastics. This is something of which we spoke last time. I won't go to the slide in my slide deck associated with this, but here we need to, excuse me, run the model not just once, but many times, in this case, 5 times, because any given run may be fairly variable. And we want a reliable indicator for a given point in this space, a given value of one parameter, a given value of another, how good the match is. Okay. So here we'll do 5, and then after it's finished those 5, it will then collect it will then assess whether it's the best iteration in terms of the mean value of the discrepancy function, of this objective function, the mean value of it. If that's the minimum mean value, we will record it as the best, and that will go here. It will kind of put it into here. Okay. This is the fundamental idea. This DS infectious historic is this value we are seeking to match, and we get it from this point here. Okay, so let's see how this runs. We've been talking about the structure of, the implementation of this. I should say, and I stand remiss for not emphasizing it, for this, we have an age-based model with a total population, some assumptions about infection probability, contact rate. These are the two that this is modifying. And then average infectious duration. Okay. And what's going on within this population? Well, we have this population of people. This population of people is composed of individuals like this, who are in this familiar natural history of infection. What's notable is that when someone's in the infectious stage, they spread infection, but they spread infection randomly across the entire population, not just to nearby people. We're not assuming a particular network by which they are transmitting just to people close by them. No, we're assuming they could transmit to anyone. Okay. Okay, so let's go try running this model. We'll actually see the calibration taking place. Let us first reflect on the fact that this yellow sequence is the historic data. That's exactly what we were looking at earlier, right? It's this data here. Goes up to just over 6,000, right? And then comes out. This matches the kind of common shape you'd expect in infectious disease network. This is the sort of exponential growth phase where more infectives breed more infections, breed more infectious individuals, etc. This is where recovery dominates. This is, and we're going to see some additional output put in here. Now, you're going to see a lot going on visually when we run this. So I just want to clue you in what's happening. So calibration progress is going to report not over time. This is not time. This is successive iterations, successive number of particular parameter combinations we've examined, particular parameter vectors we've examined. And for each of them, we're going to have a current objective function match that shows what the objective was after that number of parameter vectors were examined, and the best so far. Down here, we're going to see sometimes savvy, which try to match model output against this. Now, for a given set of parameters, the parameters are going to be shown up here, shown here, excuse me. We will actually see several attempts at matching this, reflecting those five successive replications, those five successive attempts at matching. This one here. 5 successive attempted matches. So for a given set of parameters, just be aware, sometimes it will have a good match, sometimes it won't. It'll take the average match for those to determine if it's the best, and it will show the best in red. So you'll see different blue ones being put down here that are different attempts for a given set of parameter values. And if the best one encountered thus far will yield to a red one. Just because a given parameter vector yields a really good match for one of its realizations does not mean it's the best, right? Doesn't necessarily mean it's the best, because some other realizations for that same set of parameter vectors, due to happenstance, might give poor matches. So we'll see a lot of activity here, and some may look like they're better than the best. But you got to realize what's shown in blue will be for particular realizations. What the best is, the best for the best set of parameters, what's the best average match to this? Is that, we comfortable with that? Okay. So with that in mind, let's run this. Okay. So what's going on here? A lot of sound and fury. Okay, I paused it for a second. Okay, we have some particular set of parameters. So still finishing up, I think so. Particular assumption about parameters we're currently exploring. The red is the best match so far. Not very good match. This is what we're trying to match again. This is the current attempt. Now, it hasn't really completed much here. The first one was a match of that average square root of the average square discrepancy was something like 1,710.4 or something like that. Okay, let's run it for a little bit more. Okay, it's exploring different matches. You'll notice it's running my cores on my cores. Okay, it's finishing successive values of these, many of them for this sequence. It may go on to run some for the next sequence, but probably will finish this first and then decide what to go on to next, would be my guess. Okay, so now it can completed a full 5. So now it's gone down to from about 1710 to about 1650. And it looks like it may have completed one more set because it's running so many of these in parallel. The best output thus far is this. It's trying to match this. Okay, you'll notice it completing successively successive attempts, successive realizations, but those are influenced by stochastics, not merely parameter values. You'll notice, however, it is making progress by and large in terms of bringing down the subjective function. But importantly, you'll notice that not all of the, even though it's making progress in the best one thus far, the best, most one found. You'll notice that there are some attempts for parameter values whose average objective function, whose average of this up here is not as good as ones we've already seen. And it's going to not go that direction. It's not going to embrace those as a good guide. It's going to say, whoa, that doesn't look as good. It's trying to get down a hill. And sometimes it's finding as it's coming down the hill, it's making progress. And sometimes it finds it's in a kind of cul-de-sac where it has to go up. And it starts going up and say, this is not fruitful. This is going to lead me back up to the summit. And it sort of comes down again. And it's trying to find a path that will lead down yet further, right? And you can see quite a few here are not going to make any progress. It's tried them and it's not found them fruitful. It's found them wanting. But it is still making some progress, and I'll continue on my journey here. Now, I will note that this said, run this for 500 iterations. In other words, 500 different parameter values. The best output thus far is still not that great a match. It finds some particular realizations that are pretty good, but the best average, it's not that great. But it is making some progress. It's gotten it down. It's about a third of what it was originally. Not quite a third, but maybe a half to a third of its original value. This is after about 26 iterations of these 500. It's already made significant progress, but you'll notice, proportionally speaking, its progress is slowing somewhat. It's not descending quite as quickly. But it's nothing to snoot at, right? It's gone down from about 1,700 to about 500. So now we're below 1/3 of the value. And the best output is starting to offer some degree of verisimilitude to the historic data. You notice it's trying to report on this best combination so far of this. Some of these it finds infeasible. It rules them out due to some constraint on the outcome. But it is making further progress. Now it's down to about 300. Okay. I'm going to stop this now. We've seen that there's some progress that can be made even in the first 50 or so iterations. We've really got significant progress. I'd like to take a critical eye towards this. I think you get the exploration, the overall idea. It's trying to be savvy about how to explore this. And the area of global optimization is its own subfield. And, there's wonderful research results that have been advanced in using a diversity of methods for global optimization that one can readily find. It is engaged in some measure of learning here. I'm going to stop this, and I'm going to take a somewhat more critical and inquiring eye towards this. So first of all, let's go examine. Let's refresh our memory for the calibration as to what it's optimizing. Well, it's optimizing two parameters over some range. That's specifying this, right? The range over which we're exploring. contact rate and infection probability. Let's go see where they factor into the model. Well, they factor in here. This rate is the product of the two. So if you're going to be varying them, it doesn't make a lot of sense to vary both of them. Really, the operative thing you can search and find, and you will find that they are used at exactly and only this place. So what's really the operative parameter, the instrumental parameter, the parameter that the conceptual parameter that matters is the product of these two. Like changing both of them, if you have one, you're going to get the same result as if you kept that one constant, you have the other. It's here, we're treating it as 2 degrees of freedom in this calibration, but in fact, it's 1 degree of freedom. It's just the product of the two that matters. That's the operative thing. So this is a mark of something that you want to watch out for within calibration. Like you want to be sensible in choosing your parameters to calibrate so that they are different degrees of freedom. You don't want to be optimizing multiple parameters where you could be optimizing one. I think it wouldn't be bad if we elected to instead optimize a different parameter, something like average illness duration instead. After all, that reflects this. That reflects the recovery. And if we want to optimize two things that are different degrees of freedom, that are not duplicative, where doubling one, keeping the other constant doesn't give the same value as doubling the second, keeping the first constant. But where they're really different, we could optimize average illness duration, right? And that wouldn't be a bad thing to do. I will go through the exercise of doing that at a basic level, but I'm not going to get all the niceties in the interface to show this nicely. But let's go through the exercise. So we go to calibration, and we're going to press ourselves, dear viewers, to this task. So let's go to the contact rate here. And we are going to leave that varying, but change the infection probability to be fixed. We're only going to have, because those are multiplied by each other, there's no sense changing both of them separately. And instead, we're going to change this to continuous, average illness duration. And we will modify it from a value half of its normal value, 15, to twice its normal value of 15, 30. We'll have a factor of 2 on either side. Its default value is 15. Saw that earlier when I selected it. And we'll go from half of that to twice that as the range over which we'll modify this. No, we don't specify a step. We'll allow it to figure out how fine-grained to make it. Okay. We'll also assume the default value of infection probability. And I just want to make sure I know what that is. It's 8. So I'm going to make it 0.8 here. Just to make its default. You notice it's starred, means it's changed from the default. Okay. So now we're going to be modifying these two. Now, it's not going to show that very nicely in the results. It's not going to report on it. Okay, now it's going to, okay. So this is where you have to deal with the nuisances. Okay. The implementation nuisances. Yes, OQ var. It's actually for this little thing here. It's an opt_quest var. It's going to be reading out this value out of that. And if I could, yes, here. This is instead of contact rate, because we changed it, it's going to be called, what was it called? Infection duration. Was that what it's called? Infection, the one we changed it to which we changed it. Was it infection duration? Was that the name? Sorry. Average. I'm going to be looking down here. Oh, it's in Maine instead. So let me find that. Average illness duration. Okay, good. So I'm going to double click on this to get me to the requisite place. And this is going to be average illness duration. Notice it's OQ var. Get rid of the C there. That was mine. So it's, all I did is I changed contact rate to be this. Let's see if it's happy with that. Again, a statement you never make within chemistry. Okay. Okay. It actually looks like it. Okay. I'm going to try that here. Average illness duration. Let me just see if that, yes, it appears to have placated. It seems to have had its expected salutary impact. Okay. Now this one is still complaining about infection probability. And so I will go back to that, but I'm going to click on this third one just to see if we can, and this should be illness duration. I was hoping to avoid this. Average illness duration. All I'm doing is I'm going through and trying to address each of these complaints. There we go. Average illness duration. And let's see if we can make it a happy camper. Okay, now it's build completed successfully. We have bent it to our will, but we still have not changed, and I feel obliged to change this label to be average illness duration. Okay, I'm going to save this. And I will say, yes. Okay. Okay. Having done that, I will distribute this. Having done that, I will go and run this. So what have I done? I've changed it to actually modify two parameters that actually have independent effect. They're not just multiplied each other. So doubling one is the same effect as doubling the other. There's really no point in separately adjusting two parameters if it's the product that matters. So here it's trying to match this using these two genuinely different parameters. And it's interesting that it's keeps on saying that they are the same value here. And I'm wondering if oh, you know what? Okay. I didn't change contact. No, that's right. Yeah. Because I changed it. Okay. I did something silly. What did I search for? I know what I did. I changed it from contact rate in one of those cases, the output from contact rate. This should have stayed contact rate on, and I stand remiss. I should be criticized. Instead of average illness duration, this should have remained contact rate. My apologies. I don't know what was what came over me. Okay. So I'm going to stop this and stop that confusion. And I am going to go and rerun this. So this is now contact rate. And I'm going to build it. And I'm going to run it. And I'm going to here have it display those. And presumably now it's not reporting the same thing each time. It's reporting different things. Okay. It was working properly. It was just reporting. It was working properly in the calibration. It was just reporting the value, same value twice. Yeah. Okay. Here we go. Those things, in case you're wondering what these are, those things were that I was changing. Those are reading out from OptQuest the value of the variable from that simulation. OptQuest is what it's being used to find the best value for it. Okay, so we are again running this with different values, and we are seeing attempts to match. You can see now the best output is still rather uninspiring, but it is getting closer even as we speak. We've already come down after seemingly a few iterations. I'm not sure why it's showing 1 here, but 12. It's come down to about 900 or something like that. Okay. So here we are adjusting these two in a more meaningful way. Before we were adjusting two things that were multiplied by each other. Now we're genuinely adjusting things that are different degrees of freedom associated with this. We're already down to about 579. Okay. So one thing that's confusing us a little bit is it's actually running simultaneously, it seems, replications or replications for different ensembles, some with one set of parameter values, some with the other. So it must be speculatively trying out parameters, running some of those while finishing up some of the earlier ones and figuring out how to go forward. But once again, we find it making progress. Okay, I'm going to show now, we have limited time left, but I'm going to make another point with this model at a higher level. And I hesitate to terminate when we're making such.
Hi, Professor. Thank you so much for this. I dropped a question in the chat.
Okay, there's something in the chat. Thank you. Yeah. Great. Where's the methodology? No, there's a I believe it's a genetic algorithm behind the OptQuest strategy. If you're interested, so OptQuest is as I noted earlier, it's a widely used engine for global optimization within operations research. It is described in the academic literature. And if you were interested, I could post a reference to a paper or two that describe some aspects of the algorithm used for finding for identifying the sequence of successive values to explore within this parameter space, as specified there. When I've checked it out before, my understanding is that it uses a form of genetic search. So it gets different best attempts and it kind of crosses them over to find new best ones. But I noticed this one broke out genetic, and that makes me wonder if what we are in fact running here is indeed a somewhat different algorithm that has combined it with other approaches beyond genetic search type of global optimization. But I will send you what we've used in the past as references for this OptQuest, for the OptQuest algorithm from the literature that describe it. Okay, so thank you for that question. Okay, so next, I'm going to stop this. And I'm going to I'm going to examine an impact of model structure on calibration. So specifically, I'm going to examine how a change in model structure or a model structure that whose dynamic implications differ from what is seen in the empirical data can affect and in fact complicate the calibration process. So here I'd like to go to the palette. I'd like to go to this agent palette, and I'd like to go to here. I'm going to add a transition from recovered back to susceptible, reflecting a possible loss of immunity. And if you want, you can prettify it, but so make it like that. Okay, so this is going to be called waning of immunity. And I will note that the total time frame associated with this model, the calibration for the model time is running at over 100 days. I'm going to make, therefore, this waning of immunity play out at a time frame that's a fraction of that. So I'm going to make it occur at a rate of 1.0 divided by 30.5. So it'll be about 1 month on average, as you might expect for certain bacterial infections that are very short-lived immunity. So waning of immunity. Rate of 1 divided by 30.5. So now people who are recovered will move back to susceptible. Now I'm going to save this as V3 here. Okay. Next, I'm going to, so what I've done is modify the structure of the model, right? But as I've remarked many times, structure determines behavior. This structure will induce behavior over time in the model. So let's run this calibration, attempt to run this calibration with this new structure. The model is different. The parameter assumptions are the same. The data set we're trying to match is the same. But what's different is the structure of the model. And the structure of the model dictates behavior. And you can see here the behavior dictated by that structure over time when we have loss of immunity. That change in structure, while modest, while just being but one of these three transitions has a profound impact on the observed, well, on the behavior that's elicited from this model. And the results of this could be expected, can be anticipated, right? That model structure just does not jibe with, it is not consistent with the observed data. And we can adjust the two parameters, contact rate and average illness duration, all we want. But we are ultimately putting lipstick on a pig. We're ultimately, attempting to square the circle, attempting to make something match that's not in the nature of things within these, what can be altered by these two parameters. And we can contort and, attempt to fit them, to fit the model with many, many assumptions to those parameters. But what we're going to find is ultimately that we're disappointed. The model initial match is uninspiring. We have a objective function of discrepancies function value of about over 1800. But what's more notable than this is that the best match that we'll secure to the empirical data will be greatly hampered by the fact that for any number of different of these assumptions, we're going to have a poor match. We're just not going to be able to make it work because the issue is not our parameters are off. The issue is the model structure is just incompatible. A dynamic hypothesis is captured by the model structure is incompatible with what we see in the empirical data. And the progress that it will be able to make is correspondingly hampered. It's correspondingly jeopardized. And you can see it valiantly attempt to match, but it just doesn't add up. And I want to bring this home at a philosophical level as well. You'll sometimes hear people saying about dynamic modeling, people new to it, well, garbage in, garbage out. If your parameter assumptions are off, the model's results will be totally off. Whether a model is good or bad is just as good as the data you feed into it. And that is not correct in a common sense of the word data. I mean, here, what we see illustrated writ large is that model structure profoundly dictates what modes of behavior are possible. Within the model structure we have right now, it's not a matter any value of these parameters will give any behavior of the model. That's not true at all. We could find the very best match for all these parameters. We could run this for a year, this calibration, and we will not find an adequate characterization here. I'm talking about for modifying these particular parameters. If we expanded, were we to expand our calibration to also match the timing with which waning of immunity occurred, if we were to define a parameter that was associated with this rate and adjust that, then we'd be talking, because we're adjusting parameters that ultimately affect the degree to which that added structure, is in fact operational or realized. But it is not the case, this myth you'll sometimes hear, that if you assume anything for the parameters, you'll get any behavior out you want. That with that, you can match any model to any data by just choosing parameter values accordingly. That's a claim I've heard. And that claim is, frankly, just, incorrect. It's frankly, flat out wrong. Model structure often much more fundamentally dictates what behaviors are possible. Parameters allow us to adjust within those modes of variation what particular behaviors are seen and how much, the degree to which we see certain things or another. But it's the model structure, as illustrated here, that's the more profound of the influences. And if we have a model structure that is at variance with structures we see in the world, if we posit waning of immunity when there is none to any significant amount in the world, if we were to posit large-scale transmission by individuals who remain infected permanently, if we were to posit that there's a long latent phase of infection, if we were to claim that there are some people who are super spreaders and spread to 12 times more people, those would all be assumptions that would make their way into the structure, and that appropriate calibration could identify the degree to which those structural assumptions are compatible with, are feasible with, and are consistent with what we observe from the world. So this change we made to the model has revealed the profound way in which model structural assumptions, in this case, the assumption of significant waning of immunity over time, jives with or does not jive with, is not consistent with our empirical data, no matter what values we associate to certain parameters. You can see before we were going down to values of the objective function below 500. In one case, I think it went below 400 earlier. Here, we're unable to proceed below 1500, despite valiant attempts on its part. So calibration is a tool not just for finding in some technocratic way the exact values of the parameters that make our model look best, and where we can find any parameter so let us match any data. That's far from the case. Calibration, beyond allowing us to identify the assumptions about parameter values to be less well known that will let the model best match the data, it may not allow it to match the data really, really well if the model structural assumptions are off. And secondly, it can help us challenge our understanding, our mental model. It can help us learn. Because remember, on the first day of class, I introduced you to the idea. A model like this does not capture the truth. But by allowing us to debug our thinking, to challenge our assumptions, to challenge our dynamic hypothesis, it helps us more quickly root out incorrect assumptions on our part and speeds us towards the truth. And an inability to match empirical data like this is not best viewed as not a failure of calibration, but a success of learning, by learning that a certain model structure just may not add up in a way that's consistent with what we observe from the world. So that's all the comments I will make today. And I will look forward to seeing you folks tomorrow to continue our journey through aspects of the systems data science perspective on dynamic modeling. Thank you.